Hi everybody. I just wanted to talk a little bit about how you could control movement along a path. This is the set of equations for a basic circular path. If I just put t on the inside, that would correspond to a constant rotation. How do we make our movement change directions or accelerate or decelerate? Here's the idea. We're going to want to replace the part on the inside with an equation that tells us what angle we want to point towards at a particular time. So if the part on the inside is just t, that looks like this. As time increases, the angle is also increasing at a constant rate. Let's compare and contrast with these other two, but let's think about them using Desmos. So here we've got cosine t sine t. When I play the animation, you can see just constant rotation. Let's go ahead and replace t with t squared for a moment and see what that does. Okay, well, you can see it actually hasn't affected the path at all, which isn't surprising, because the path is being determined by the cosine and sine parts. The only thing I've changed is the input to cosine and sine, and that controls not the actual xy coordinates of my path. That controls the angle that my point is at along that path at different times. So if we want to see what effect the t squared has, we actually have to watch the animation. So here we go. Let's go back to the beginning. So you can see that this corresponds to acceleration. Let's jump back to the page and think about why that makes sense. When the angle was just being given by t, we have a linear graph. And remember, linear growth just means that for every increase in x, you have a constant increase in y. So think about the meanings of x and y now. For every 1 additional second, my y value is going up by 1. But my y value here isn't describing the y coordinate, it's describing the angle, because this equation is going to go on the inside here, which describes angle. So what that means is every additional second, I'm rotating by the same angle. And so hopefully that makes sense that you would be rotating at a constant rate. You can think about each one of these kind of equal angles as being an increase in 1 second. So 1 second I rotate that far, and then I rotate by the same amount, same amount, same amount, same amount, same amount. If you think about how I would rotate faster, what would that graph look like? It would just be a steeper graph. For every additional second, I am rotating my angle by a larger amount. So the slope of the angle graph would be steeper. Okay, so let's contrast that with this situation. Here, let's think about the difference between, let's say this is 0 seconds and 3 seconds. And then let's say this is like 6 and 9. This is like way up here somewhere. So between 0 seconds and 3 seconds, I've got an increase in 3 for the time, but if you look at how much my angle increased, it's a very small amount. So that means as at the beginning of the animation, my angle is only rotating very, very slowly, because each additional second, there's only a small increase in angle. But then once it gets going, here is still an increase in 3 seconds, but now if you look at how much the angle increases, it's by a lot. And so that's why that curvature creates an acceleration. It's because as time increases, the amount the angle increases is larger and larger and larger. Okay, maybe you can guess what this one is going to do. Go ahead and imagine it for a minute. So I'm just going to create an equation that has that general shape. So here, here's a quadratic equation with x-intercepts at 0 and 10. So that would make 0 and 10. I put a negative out front so that it would be upside down. So, yeah, I mean, you could calculate what was the maximum angle here, but let's just have Desmos do it, because what we're doing right now is a little bit more conceptual. Rather than trying to type that equation on the inside here, I think it's nicer to just define it somewhere else. So we'll do t minus 10, and then I'm going to take that a of t, and I'm going to paste it on the inside here. So that way I don't have to retype my same equation 4 times. And in fact, I can sort of forget about this part up here, and I can just experiment with my angle equations down there. The only thing I want to do is I don't actually want to display the curve there. If you're wondering why does this look like a line, it's not actually a line. You can zoom out, and it's actually a parabola. Okay, so I don't want to look at that right now. Let's go ahead and back up here. Oh, Y. Hold on. Oh, I know why. So I need to use capital T's for that one. Okay, so let's watch what happens. I play it, so I'm rotating, but I slow down and then go the opposite direction. Let's divide it by something like 10. Let's divide it by like 12 and do it again. Oh, no, let's not. Good thing I planned this video, huh? Okay, so I'm going to divide it by 3. So now I go a little more than a full revolution before I change directions. So you could experiment, but rather than use Desmos to experiment, here's what you're really going to want to do. You really want to think carefully about what do you want this maximum angle to be, and what time do you want it to happen at. So you'll think carefully about what this graph needs to look like. That'll give you the equation that you want, and then you can plug it into Desmos to verify that it makes sense. If you wanted to use these ideas to describe the 3 phases of an amusement park ride, you could start off at an angle of 0, or an angle of whatever you want. Then you'll have a phase where for some amount of time, the rotational rate will be accelerating. So remember, you wouldn't want a line in that case. You'd want something that has an upward curvature. Then you'll enter some phase of the ride where it's going to be rotating at a constant rate. And there you probably will want a line of some kind. So like upward curve. And then for the deceleration, I'll let you think about the deceleration. But we're going to end also at some angle. If you want to end at the exact same position that you started at, like let's say I'm going to start at an angle of 0, if I start at an angle of 0 and eventually end up back at an angle of 0, that's going to have the shape where I'm rotating counterclockwise, but then at some point I rotate the opposite direction to get back to an angle of 0. A lot of rides don't actually stop and change direction. So what you have to realize is that any multiple of 2 pi ends right there. So up here I could have 100 pi. So I could have, some kind of upward curve and then some kind of line. And then if I end here at 100 pi, I'm still ending at the same position I started at. But the whole time my angle has been increasing. So how do you get an upward curve and a line and a mystery curve that will decelerate? If this is really going to be a line, then you're going to need a piecewise defined function. You could have some function that is curved the whole way through that does this, but I think for the best bet to give you maximum control is going to be to define 3 separate intervals and have 3 separate equations to make it piecewise. So that's why in your final equation you probably want a of t here, because how are you going to write a piecewise equation on the inside of another equation? The answer is you're not. You're going to define a of t separately, and then in your x and y of t, you're just going to have a of t referenced there. I hope that this was helpful.